Welcome to the lecture on turbocharging AI for NPUs, where we'll walk through practical model optimizations that unlock massive efficiency gains. In this presentation, we'll cover techniques like quantization and pruning, compiler-driven acceleration and memory management, and how these combine to make neural networks run faster and leaner on dedicated NPU hardware. This slide explains NPU architecture and why hardware-software co-design matters. Systolic arrays, INT8 pipelines, and weight stationary data flows are built to keep tensors local and maximize parallel compute, while model techniques like pruning, quantization, and operator fusion are adapted to that structure. Together, they drive much higher max per millimeter squared, reduced power, and simplified data movement for real efficiency gains. Reducing precision from 32-bit float to 8-bit integer has outsized benefits. Model size can shrink roughly fourfold. Throughput typically doubles and energy per inference drops significantly. To preserve accuracy, we use calibration, quantization, unaware training, and percentile scaling, and we align data types with NPU constraints to avoid costly runtime dequantization while keeping inference fast and accurate. Channel pruning paired with toolkit optimizations shrinks graphs by 4 to 10 times by removing filter groups and then retraining to recover accuracy. Toolchains like VLA and Tau automatically adjust memory footprints and expose wider parallel lanes on accelerators, so the pruned model runs efficiently on hardware without manual retuning and with minimal accuracy loss after fine tuning. Layer fusion eliminates intermediate DRAM traffic by merging conv, batch norm, and ReLU into a single fused kernel that maps directly to the NPU. Compiler fusion rules from Vela, TensorRT, and similar tools enable this transformation, cutting latency by around 30 to 50% and saving power and SRAM by keeping data on-chip instead of shuttling it through DRAM. Architectural techniques like depth-wise separable convolutions, inverted residuals, and sparse attention dramatically reduce multiply accumulate work, often by an order of magnitude without hurting accuracy. Aligning model blocks to NPU tiles, as with MobileNet v3, efficient NetU Lite or TinyYO Low, ensures high tile utilization and efficient execution on existing hardware, avoiding the need for a silicon redesign. For microcontroller class NPUs with tiny RAM and strict power budgets, strategies such as sliding window inference, ping-pong buffers with compute, data overlap, and layerized checkpointing trade extra recompute for big memory savings. These patterns sustain practical outcomes like 30 frames per second for speech, or about 15 frames per second for QVGA vision, on low-power hardware using very small working sets. Dynamic classifiers reduce latency by allowing confident inputs to exit early, skipping 20 to 40% of layers when a confidence threshold is met. Lower confidence cases proceed through remaining layers for full results, while system-level tactics like batch size 1 scheduling and interrupter-driven wake-ups further lower average latency by roughly 30%, keeping peak accuracy for safety-critical tasks. Mixed precision training combines FP16 forward passes with FP32 master weights to accelerate training by about 1.4 to 1.8 times while retaining convergence, and fused attention plus communication overlap cuts step time dramatically. By overlapping communication kernels with computation and enabling kernel queuing, NDRTN step time can drop from around 48 seconds to about 26 seconds on multi-crew setups. Auto-hybrid parallelism balances compute and communication for billion-parameter models by combining pipeline parallelism and tensor splits, raising micro-batch size and halving tensor partitions. Multi-shard dispatch with gradient overlap further reduces idle time across shards and achieves measured speedups, for example, a 1.41 times overall speedup, versus a baseline lowering total compute hours for large jobs. The optimization toolchain routes quantized and pruned graphs through VLA, TAO, ONNX runtime, and TVM, then applies layout and tiling passes before emitting NPU binaries, forming a repeatable flow. Continuous profiling with advisors measures latency, SRAM, and flash usage and power, pinpoints remaining bottlenecks, and guides iterative fixes until the design meets silicon sign-off criteria. The practical NPU optimization workflow starts by picking lightweight backbones, then quantizing to INT8 and pruning filters, fusing operators and streaming tensors, enabling early exits, and finally benchmarking on real silicon to iterate. When applied together, these steps commonly produce consistent outcomes: about 4 times throughput, roughly 3 times memory footprint reduction, and production-grade accuracy preserved for deployment.